Hi, good evening, everyone. Thank you for joining us this evening and sparing your time. We are joined by our panelists and we will begin shortly. Thank you.
Yeah, Kushagra, we need to go through the ASHRAE Code of Ethics as well.
Yeah, sure. Good evening, everyone. This is Kushagra Duneja from ASHRAE Rajasthan chapter. And with me, I'm joined with my co-host, Mani Khanna, who is from ASHRAE Chandigarh chapter, and Kishan, who is from ASHRAE Jaipur chapter, who is also the supporter of this webinar. Let us first go through the ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which will exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflicts of interest. Thank you again for joining this evening and sparing your time. The topic for today's webinar is Insights into ASHRAE 90.1. It is indeed a very interesting topic and of interest to a lot of the engineering community. The webinar is jointly organized by ASHRAE Rajasthan chapter and ASHRAE Chandigarh chapter and is supported by ASHRAE Jaipur chapter. Next slide. So ASHRAE is a global organization, as you all know, and the full form of ASHRAE is American Society of Heating, Refrigeration, and Air Conditioning Engineers, and it has a presence globally. We are joined by our presenter, who is Samuel Mason, who is an engineer based out of the US, and we are collaborating with him from the Indian chapter to conduct this webinar. To give a brief intro about Samuel's profile, he specializes in building retrofits, energy service contracts, financial and cost benefit analysis, construction management, energy analysis and building energy simulation, HVAC design, environmental design, daylight analysis, and renewable energy analysis. He is a licensed professional engineer in the US, in the states of New York and Colorado. He's a lead AP BD plus C and ASHRAE certified BEMP, Building Energy Modeling Professional, and also serves on the lighting subcommittee of ASHRAE 90.1. He has the knowledge of several software, including Equest, Energy Plus, IESVE, and so on, and has worked on several building types, including existing building retrofits, laboratories, academic buildings, commercial and residential towers, museums, and healthcare buildings. ASHRAE Rajasthan and Chandigarh chapter are the two young chapters of ASHRAE, recently started in India, and the strength is exceeding 50 in both the chapters. And today we also have Kishan from ASHRAE Jaipur chapter. Mani, before we move forward, would you like to say anything? Okay, hearing none, let us move forward. So let us begin with the webinar, and I will request Sam to share his presentation now. I'll just make you the presenter. Mani, I think you will have to switch because you are the screen. You are broadcasting right now. Yep. Okay, Sam, over to you.
All right.
Thank you.
Thanks, Kush. Um, all right. Kushagra, can you confirm that that is visible? And
Yes, your presentation is visible and you're audible.
okay, all right. Well, thank you everyone for joining today, wherever you are in the world. Like Kushagra said, my name is Sam Mason. I'm a professional engineer out of the US, and I mostly am focusing on energy analysis for buildings these days, and a lot of that is related to building retrofits. And today we're going to talk about energy efficient design for buildings and how ASHRAE 90.1 plays into that. And we're going to look in more detail at Appendix G, which is the performance rating method of ASHRAE 90.1. Copyright. Anyway, we will share the presentation as a PDF later on, so we will make it available. Skip through this, like Kushagra already introduced. Our main focus last line is sustainable, cost-effective solutions for buildings, and that's what we use energy analysis for, is to find the most pragmatic and cost-effective solutions, and we'll give a few examples of that today. We work on a wide variety of new construction, existing facilities, and most of that work is focused in the United States, though there are a few international projects we're still working on. So a few examples, some older buildings, some new buildings. We tend to find that the existing buildings have a little more are a little more interesting, in that you have bigger constraints to deal with as you're trying to make a building more efficient. So we'll throw in some of that information today. So the outline for today, we're going to look at 90.1 as a general guidance and standard, and what actually 90.1 entails. We'll look at overall overview and application of ASHRAE 90.1, and then we'll look at Appendix G specifically and run through each of the items within Appendix G and how that applies to the design of a new or a major retrofit. And today I'm going to look mostly at 90.1 2013, which is sort of the most widely, I'd say, adopted version of 90.1, currently used in sort of the major metropolitan areas of the United States. This is changing. There is a 2016 version of the standard and a 2019 version of the standard, both of which, well, 2019 is not being sort of used yet, but 2016 is definitely becoming more popular. And New York City, in the next 3 weeks, will adopt a version of 90.1 2016. There's also New Jersey is adopting it as well. But today we'll look at 90.1 2013 as sort of the current version that's being used most widely. So let's just quickly look at the overall historical efficiency improvements of 90.1. So 90.1 was first created in 1975, and the way that this is set up is that it's a normalized against 100% energy consumption, with 1975 being 100. And you'll see that there were various sort of permutations and changes to that as we moved along. The major first change was 1989, when there was roughly a 15% improvement in the overall standard in terms of energy efficiency. 99 and 2001, there's also some minor changes. 2004 was sort of the next big change that you saw, and it dropped another roughly 20% in terms of energy efficiency as compared to the 1989 standard. And that was sort of a big change when there was a lot of things added. Appendix G was first added in 2004, which is what we'll talk about today. And then there was also, again, 2007, which is still used in some parts of the US. 2010, which is still the reference baseline for LEED. So if you're doing LEED energy analysis, that is still the reference baseline. Today we'll talk about 2013, and obviously 2016 now is being adopted by local municipalities, and 2019 was just recently published. We just released that version a few months ago. So anyway, we'll talk some more about that, but that's just sort of reference. And you'll see that, you know, at 2013, we're roughly 50% better than we were at the 1975 standard. The intent of the standard is to drive energy efficiency towards a net zero. I mean, that's the overall goal of the 90.1 and ASHRAE generally for commercial buildings, is to be net zero. And obviously there's some limitations to that, including cost and, you know, just feasibility for certain climate zones to get to that point. So there's, you know, discussions of what the next steps will be for the next iteration of 90.1 currently going on. But renewables do become part of the standard. There's a minimum amount of renewables required going forward. So what is Appendix G and 90.1, you know, generally used for? 90.1 as a standalone is not a code. It is not an energy code or anything of the sort. It is a standard. It can be adopted by a municipality or a user group to become a code. So you know, this graphic is intended just to show that, you know, for instance, Appendix G of 2010 is used by LEED, and that is the benchmark that they use. The previous version of LEED was using 2007 Appendix G. 2013, which is what we'll talk about today, is used by several states for compliance. It's also used by several municipalities, so local cities that use it for compliance. But you'll notice that there's still previous versions, 2007, 2010, that are still being used locally in the United States as compliance path to show compliance with energy code. So again, 90.1 is a standard. If a local municipality or a state even adopts it, then it can become part of the code. And in most cases, when it is adopted by the user, it is modified for their specific use. So what happened in 2016, we won't talk about it in detail today. We'll have another webinar about 2016 because it's a slightly different approach in terms of how you look at the performance rating method. But 2016 was aimed to you know, create one standard baseline that's not going to change going forward. So what it's done is it has referenced back to the ASHRAE 90.1 2004 as the reference baseline, and it's created a building performance factors which effectively change how much better you have to be than the reference baseline to show compliance with the standard. So, you know, whether you're a commercial building or a sorry, and I totally realized I skipped over questions. I will stop one sec. Well, there's going to be breaks for questions as we go through. So when we get to that point, Kushagra and Mani will field questions, and we'll try to answer as many as we can. But there are breaks.
Definitely, I would suggest everyone to kindly share their questions through the question box. Also, I'm seeing a lot of people saying there's no audio. I think voice is pretty clear for us, but if you're facing an audio issue, please reconnect or check your network settings. Thank you. Sorry, Sam.
No, that's fine. I'm going to double check my audio just to make sure that it's, yeah, it looks to be fine on my end. I'm not sure. I
think we're good.
Okay. I'm going to keep moving because we don't have that much time. So again, ask questions through the chat box and we will answer them as many as we can as we get to the breaks. So again, as I was saying, 2016 version of the standard changed a bit in that, you know, it set a reference baseline to 2004, and it now uses a total cost index and a building performance factor. So each building type has a building performance factor that dictates how much better you have to be than the standard to meet the 2016 version. So again, it creates a percentage better that you have to meet in order to show compliance. We won't talk about that today, but so we'll jump right into overview and application of 2013, and then we'll get into each individual section. So what is the purpose of 2013, of 90.1? So 90.1 overall purpose is to show the relative performance of a design building, so a building you're working on, against a minimally compliant ASHRAE 90.1 building. So ASHRAE 90.1, the key takeaway here is it is a minimally compliant standard. It sort of tells you the minimum that you would have to build to in order to meet the requirements of the standard. The way that we generate and modify and put the language together for 90.1 is that we have a large majority of stakeholders that come to meetings 4 times a year, and we talk about the standard and we understand what's going on in the building world and building systems, HVAC, lighting, envelope, and we modify the standard as to what is the current standard building practice. And it is updated every 3 years, and it's intended to be current when it is published. So it's ever evolving sort of standard in terms of what is there. Again, it is mostly North American centric. We do have stakeholders that feed in from Europe as well, more specifically for lighting, although HVAC is now becoming more commonly used from Europe as well. But again, international application is a little difficult, again, depending on local construction practices and availability of equipment. So, sometimes what's considered current, in some places might not necessarily be current in other places. And, putting a water-cooled chiller in Jaipur, for instance, probably is not going to fly with a building owner, although that might be standard practice in the US for a large, office building or a hotel. So we're trying to work through how to make it more applicable in those senses. But for now, it's a little bit difficult. Again, in terms of function, it's not intended to be code compliance. As I mentioned, it is a standard. If it is adopted, it can become a code. But as it stands, it is a standalone standard. And it creates this baseline, so it creates a minimally compliant baseline, which we'll talk about in more detail today, of using Appendix G, which allows for credit or penalty against your actual design parameters. So it is a trade-off once we get into Appendix G. So what does it actually look like? There are 6 sections that have mandatory provisions that must be met regardless of how you're showing compliance with the standard. So there's envelope, HVAC, domestic and service hot water, power lighting, and other equipment. So there's 5.4 through 10.4, which are all mandatory. And then there's compliance options. So either you can go through a prescriptive, essentially a checkbox exercise to make sure your equipment or your envelope or your lighting system meets the minimum requirements, or there's 2 performance paths: energy cost budget, which is Chapter 11, or performance rating method, which is the Appendix G. And today we're going to focus on Appendix G, but I will mention energy cost budget has its own merits in that it's a very similar approach to Appendix G. It just has some slight changes in terms of how you can trade off between systems. So Appendix G is a full trade-off where you could have 100% glass box building, and you could use other systems to make up and save the energy for those losses. All right. So if you follow prescriptive, there are a whole other set of sections which we won't go through today, but 5.5 through 10.5, which give you prescriptive requirements for each building system that you must meet in order to show compliance with the standard. Again, it tells you an R value for your windows and a certain lighting power allowance by space type. Energy cost budget, again, like I said, is very similar to Appendix G. Energy cost budget is based strictly on a better than cost, and you can only trade off between systems that are being installed or renovated, so you can't take credit for existing conditions. So there are ways to approach the application of energy cost budget versus Appendix G. Appendix G, like I said, is a full trade-off. You can trade energy from any system to any other system. The main reason to use Appendix G, and as we use it for LEED and for other things, is to show how far you're exceeding the code. You know, where you're going to really improve upon the prescriptive requirements. And for 2013, you know, there's no specific requirement to exceed the code to say, or to exceed the standard to say that you're meeting the standard. Although municipalities have adopted a percentage savings that you must meet. Like I said, in 2016, that changes, and we'll talk about that next time. So today we're going to talk about Appendix G. Run through it. This is just all of the tables that are in Appendix G reference back to specific sections within 90.1. So this is sort of just a reference. When you have a copy of this presentation, you'll know where to go look to find these pieces. So what does this look like from a modeling point of view? The first step is to create a baseline, which is representative of 90.1 2013 minimum performance requirements. So it is the mandatory provisions plus the stipulations in Appendix G. So essentially, it is your baseline. If you were to meet, if you were to model, this is your standard building that has, you know, fixed wall assemblies, fixed lighting power, fixed envelope. That's all dictated by the prescriptive requirements of the standard. And then you create a proposed model, which represents the actual design building. So it might be slightly different in terms of systems, in terms of amount of window, but the few things must be the same. So you have to have the same orientation. You can't take credit for siting on your building, though we'll talk about rotating the building. You must have the same zoning, and you have to have the same operational schedules. So there are some limitations to this one in terms of lighting and plug controls, which we'll talk about. So in terms of zoning, what does this look like? Zoning shall be equal. You have zones that reflect different space types, and in not all cases will a specific zone be equal to a thermostatic zone in the building. So it should follow the HVAC design generally, but you can combine zones when you're running through this process. If you have a core and shell type building, which this is sort of more representative of a core and shell, you need to show roughly a 15-foot perimeter zone. That is what's dictated by Appendix G, and separate your perimeter and core zones. So otherwise, it's fairly open to interpretation. If it is residential, which the standard is applicable for residential buildings that are over 3 stories, the general zoning path is one zone per dwelling unit. So you're not going to split up a dwelling unit into a kitchen and a bathroom and a living room and a bedroom. It'd all be put together as one, unless you're looking at very, very large residential spaces, but generally one zone per dwelling unit. So what does that actually look like? This is an office. You have open perimeter office, you have open core office, and then you have some sort of core spaces and conference rooms. But this would be, appropriate for a PRM type model where you wouldn't have to actually get into the details of breaking down an open core office into several different zones or perimeter offices into several different zones. So schedules, there are a set of prescribed schedules that can be used for this type of analysis that are in the user's manual. And so it really is only applicable for a certain small number of buildings, although for 2019, this I think it's expanded to 15 building types. But it's just a starting point, and if you know the actual operational schedule of your building, you should use those. Again, as long as it's consistent between the baseline and the proposed model. There are also reference schedules in Energy Star, particularly if you're doing multifamily buildings. There's schedules that should be used there. And then ComNet also has some schedules. And again, like I said, if you have your own schedules, because the building will operate a certain way, please use them for this analysis because it'll be more realistic. What the standard says is it must be reasonable and appropriate. So that's sort of up to your judgment. So here's just an example of what it looks like in the user's manual. This is for an office. So for every hour of the day, they have a fractional load component associated with occupancy, lighting, receptacles, whether your HVAC system should be on and off, service hot water loads, and elevators. And again, each of these are a little bit different, but it doesn't dictate your thermostat set points, for instance. So that's going to be something that's going to be specific to your project and whether you have a setback temperature or not. But for each of the major building types, again, there's 10 of them here. There is a set of schedules that you can use, so it's a good starting point. So that's the high level overview. And then we're gonna quickly run through all of the individual sections, but if there's any immediate questions.
So I think, Sam, we have a few questions now. The
Sure.
first question is, how does guideline 36 and 90.1 relate with each other?
You know, I am not familiar with guideline 36, but I will look it up as we're here.
Definitely. So maybe this question was from Gideon Solomon, and you can write to the ASHRAE ID that I've shared, and we'll get back to you definitely. The next question is for green buildings. Yeah, go ahead.
Sure. Oh, I was just gonna say, regarding that question, if you send an email, my email's at the end, send me an email and I'll find out for you.
Sure.
Okay. Keep going, Coach, sorry.
The next question for green buildings, designers require 19 watts per GPM for condenser water pumps. Is that the basis or conditions applied to it, or is it a generic requirement irrespective of size and application of building? This question is by Vikram Bansal.
Okay. The way the standard is written right now is it is, if you have a water-cooled cooling system or heating system, if you have heat pumps, that is the maximum allowed if you're doing Appendix G modeling. So 19 watts per GPM is the maximum that you can have in the baseline. Your proposed design can be much larger than that if you want, but you need to make up the energy elsewhere. If you're doing energy cost budget, which again is not allowed for LEED, but it is allowed for other purposes, it is more of a trade-off where you have a limit. You know, it can exceed 19 watts per GPM, but you can take no credit for your improvement. So say if you're lower than 19 watts per GPM, you won't get any credit. But yeah, it is the minimum requirement if you have a water-cooled condensing system.
Great, thank you. The next question is from Dheeraj Patil. His question is, how can we integrate the building code and energy simulation software?
Sorry, integrate, what was the first part of that question?
How can we integrate the building code and energy simulation software?
The code? Was that the
code and the software?
So
I think what he means is how to relate both of them.
Yeah, so I guess, you know, there are certain softwares that are integrating the code requirements into the software itself, where you can generate, you know, compliance documentation directly. I think, you know, it's sort of yeah, I don't know, it's sort of a give and take in that sense, depending on the type of software you're using. So, I mean, for example, in New York City, you know, if you're doing prescriptive, you can use what's called ComCheck, which is a commercially available, you know, software that you can pick your baseline and fill out all of your details, and you can decide whether or not, you know, it'll kick out a compliance sheet at the end. If you're using IES, for example, it has compliance paths built in as well, both for 90.1 and for other standards. So it sort of depends on the software you're using, whether it's applicable. I mean, building simulation is used to drive the development of the standard as well. So I'm not sure if that was the intent, but it is intimately involved in this whole standard. So.
Right.
All right, Chris.
The next question is from, sorry.
I think we got to keep moving, man. I'm sorry. I was going to say 2 or 3 max, and then we'll.
Yeah, so we'll take one more and then we'll jump in to the presentation. So the next question is from Prajakta, who says, we use this standard in India to comply LEED and IGBC requirement. As you stated, it might not be applicable to all countries. What is your opinion of using it for India, or using local energy standard is better?
Yeah, I mean, it's a good point. The standard was not written for the Indian climate, or specifically anywhere, within the Indian climate. I mean, I think it's hard to say, because I know that that's what LEED requires as the baseline, and it's hard to show compliance with it. Yeah, it's a hard approach. I mean, it's something we talk about in the 90.1 committee all the time, of how do we make this more universally applicable. But every country has their own approach to building design and construction, so it's a little hard to account for all of them. I mean, I guess that's the intent, is to try to make it as level a playing ground as possible. That being said, it's having cooling towers and things like that, I tend to find, are the one place where the standard deviates from a lot of what local design would move. So hard to say.
I think we can go on to the presentation.
Okay. Yeah, and if you have further questions, shoot me an email at the end, and I'll get back to you. So
sure.
So the next 4 sections are running through the actual components of 90.1, and I'm going to move fairly quickly through these because we don't have a whole lot of time. So again, we'll stop for questions. But so what does this look like from an envelope point of view? So there's 4 mandatory provisions: air barriers, rated leakage for your systems, which again, if you're outside of the US or Europe, getting rated fenestration is tough. So again, it's sort of hard to show compliance. Weather seals and vestibules, which we won't go through in much detail. But if you're doing performance rating, there's some general modeling requirements. You have to have equivalent dimensions and equivalent geometries, as noted. 2013 was the last time that you will be asked to rotate the building, but you'll notice if you do LEED modeling, you have to rotate your baseline building 4 times to account for each orientation. And then again, other specifics. The only really important one out of all of these that makes the biggest difference is that each climate zone and building type has a specific envelope thermal performance that is required. So if you're in climate zone 1A, you have a insulation factor required for your roof and your wall, and you have a certain performance of your window in terms of U value and solar heat gain. So that's the biggest takeaway. In terms of proposed, there's a lot of small, minute details that you can look at, but the biggest idea is to simplify your envelope. If if you have a bunch of small turns and facade orientations, you can simplify that as long as you can use a 45-degree rule between your surfaces. Again, the big one on the proposed side is that you must account for your uninsulated assemblies. And as we get to the newer version of the standard, you'll see that there is a thermal bridging component that's being added in the 2019 version of the standard. But again, it needs to be realistic for what you're actually including. Won't go into much details, but just some examples of shading. The proposed design can take credit for shading, baseline does not. In terms of opaque assemblies, if you're doing PRM, it is a fixed baseline for your envelope. It is a steel framed wall. It is a continuous insulation above deck roof. I won't go through any of the others because they're not generally applicable, but so regardless of how you're constructing your building, whether it's a mass building or a wood building or whatever else, you have to compare against these baseline types. The one change that you will notice if you do LEED modeling for 2010, 90.1 2010, is that you can take credit for existing envelopes that are worse performing than the standard. When you get to 2013, an existing envelope must be modeled as compliant with the standard regardless of what the condition is. So in the proposed design, you would be taking a penalty if your wall performance did not exceed the standard requirements. So we find this a lot in New York City, where we have old brick buildings that are uninsulated, but we have to take a penalty for that against what the baseline model is. And that's just, you know, something you got to deal with. You got to make up that savings elsewhere. So what do the tables look like? This is just an example for climate zone 4, you know, where you have to pick through and, you know, pull out your assembly values. Won't go through the details. You know, here's just a few examples of some sort of project related details of a soffit, you know, how you can exceed code by doing 2 layers of insulation, you know, what your below grade and footing insulation would look like. Example of, you know, continuous exterior wall insulation. And again, those are ways that you can improve upon the envelope. In terms of windows, depending on the type of building, you have a maximum window and skylight area. And then there's also performance assigned values. So you have U value, solar heat gain, and visible transmittance, again, by climate zone and type, whereas your proposed design will be your actual windows and your actual skylight area. And it must account for the entire assembly, so including frames. So this is something that is being checked more and more by building officials and code officials, and LEED as well, is to make sure that the assembly values are being used for windows. So it is something that is being checked in more detail now. So what does this look like for, say, a reference building? You have a large office building. You have a baseline allowance of 40% window to walls, a 40% window area. In the PRM method, you can design however much glass you want. So say in this case, you have 65% glass. This will be your comparison. Obviously, you're going to take a penalty for your proposed. You're going to have more glass area, more, you know, heat loss, more heat transfer through your facade. But again, this is why people use the PRM method, is that you can trade off and you can build a glassier building and still show compliance. So this is the table, you know, by building type now in 2013, where you have, depending on the size of the office, say if you have a smaller office, you're only allowed 31% window to wall. At a large office, you get all the way up to 40. So in the past, it was 40% for all buildings. You notice this is very different now for some smaller and other building types. Specifically, one that we're running into now is warehouse, where the maximum is 6%. So before you were building a warehouse with 40% window to wall to show compliance with the standard, and now you get 6%. So it's a pretty big change. And again, there's a similar table for your baseline fenestration values. So, sorry, you know, depending on the type of framing that you have, you will get a maximum assembly U value. Solar heat gain and visible light transmittance are, again, dictated by climate zone. And in terms of skylights, you know, 3% is the maximum allowed. So anything over 3% you can design into the project, but you'll take a penalty for it. So just some examples. This is an old building, Bell Laboratories, that we're working on in New Jersey, that, you know, has roughly 85,000 square feet of skylight area. So I have a few slides in here about 2016. So 2016 looks very similar to 2013 for this portion. But again, there are, I believe it actually is the same for 2013 as it stands now. So there's a maximum allowance of window to wall ratio per building type. And just some notes about what happened between 2004 and 2016 in terms of stringency of the standard. So going back and referring back to where we started, we'll only go back to 2004 as a starting point here, but you know, the reference I like to use is New York, of what happened in New York. In that 2004, you had an R15 roof is required, and now you have to have an R30. So it's roughly doubled in terms of the prescriptive requirement for what you have for roof insulation. Similar to walls, you have, you know, again, you can look through all these in much more detail, but a steel framed wall in the East Coast of the US, it was a R13, and since then it's only gone up that you need to add 7.5 inches or R7.5 continuous insulation. So there hasn't been much change since 2007 there. Again, some of the other climate zones and some of the building types have changed. Similar for U value, that you have, pretty substantial changes here in that, you had U values of 0.6 and 0.7 in 2004, and you see now you're getting down into 0.3, 0.4. So pretty substantial reductions there, 30% plus. Same with solar heat gain, is that they've come down a little bit over time and they've sort of gone back and forth, but you'll see in 2016 that number has just generally come down, and that's due to overall increasing temperatures as we see in the climate models. So solar heat gain is going to go down most likely in the future as well. So what about infiltration? Again, the simplest way to deal with this is that they need to match. The only way to prove it is that if you can prove that you have lower leakage than the baseline through whole building testing, which generally is cost prohibitive. So questions on envelope. I'm going to keep moving quick. We'll do 2 questions if there are any.
Sure, there are many. So specifically on envelope, I'll just take questions as they came rather than just focusing on the envelope.
Sure, that's fine. We'll do 2 questions and we'll keep moving.
Yeah. Are there any normalization techniques being taken into consideration? If any, could you please briefly discuss? This is asked by Jayant Sharma.
Normalization? I'm not sure. I mean, there's a lot of ways I could interpret that. I'm not really sure what the
question means.
Yeah.
The next question is.
Email. That's the best way to deal with it. So.
Sure. For the residential, the application requirement is different. Is the zoning as one zone per dwelling unit accurate in case of residential? This is asked by Pallavi Ballamudi.
Generally, it is acceptable. Like I said, there are variations in that. If you have a bunch of dwelling units that are facing the same orientation that are roughly the same size, you can group them all together in the model. But generally you're going to have one per unit. And that's, there's been a lot of modeling done to prove out that there's really no difference in the energy consumption if you model all the individual zones within a dwelling unit versus one large zone. So, again, it is specific to a project where you might have, if a dwelling unit is facing 2 separate orientations within a building, so it has south and west facing, say, you might need 2 zones. But, for relatively small dwelling units, like say up to, not relatively small, but say for normal sized dwelling units, say up to 500 or 600 square feet, you're going to have one zone per unit. If you're getting to very large, like sometimes in New York, we see these apartments that are 10,000 square feet. In that case, you might have multiple zones, but generally for a multifamily type building, you're going to have one zone per dwelling unit.
Right. Sam, one more?
Yeah, so one more.
What is the basis for 19 watt per GPM for pumps? This is asked by Saurabh Goyal.
Yeah. I would have to dig deep down into the 1989 when it was first discussed, but it is, I'll have to look and see exactly, but I believe it was, there was a whole bunch of buildings that were studied and they pulled actual data from, I don't know, 50 or 60 buildings that had large water-cooled condensing systems. And that was where they ended up as the average. If you designed in a relatively efficient manner, that's where you ended up as the average. I can dig and find out the exact reference. There's a data point for it. I'll just have to find it. So,
Perfect. I think we can move forward.
Okay, so keep moving. We are at 45 minutes, so we'll move quick. So next section is lighting and power. I'll start with power quickly because it's it's a small section, but it has a large impact. So there are two mandatory provisions within power that generally will affect a model if you're doing performance rating method. One being automatic receptacle controls. So this requires 15% of your small amperage, low voltage receptacles to be controlled. So again, this just is sort of listed as 125, but it could be anything from 100 to 140 really. The dictation is nothing over 20 amps really. So this is going to be your small miscellaneous electrics, which will be your computers, copy machines, things like that. Again, there's a lot of pushback to this, and the energy savings are variable depending on the type of building and how people are using them. But it is in the standard, and in 2019 we had a lot of conversation about this, and we were talking about providing alternative paths. It's not going away, it's staying there. So it is something that needs to be designed in, although a lot of municipalities are writing this provision out of the code when they adopt it. So New York City for the last 3 years has allowed you to not do this. Although with the new version of the code coming out in New York City in 3 weeks time, they are putting it back in. So again, if you're modeling this, if you have the plug load controls, the schedules should reflect that, and they'll be the same schedules. There is a lead approach and there's an interpretation from lead which allows to say that if you're not including automatic receptacle controls, you can take a 20% penalty for the spaces where you have plug load controls required. So that's a reference point, which we're using for a lot of lead projects in New York City, actually, funny enough, that are not doing plug load controls. The other mandatory provision is energy monitoring. And again, you're not really, to comply with the standard, you need to do this. Not that many people are actually doing it, but it says you need to monitor total electric, and then a breakdown of each of your major systems. So receptacles, exterior, interior lighting, and HVAC. You also must separately monitor tenants, only if the tenants are over 10,000 square feet. So again, for a large building, this could get quite costly and must be considered during the design of the building. But you have to store it for 36 months, which also is you need servers or cloud storage to meet the mandatory provision. So that's it for power. In terms of lighting is probably, lighting and HVAC are the most complicated. Lighting controls being probably the point where most people have the most questions about how the standard should apply when you're doing modeling. So generally there's 3 levels of mandatory provisions. There's an automatic shutoff provision, some level of control, whether it's occupant or daylighting. And then there's a set of schedules where you must have separated schedules for architectural lighting versus decorative lighting. So in terms of modeling, there's 2 approaches. You can use building area, which is 1 lighting power density for the whole building. Again, there's no trade-offs, no allowances here. It is simplified. It makes things a lot easier. So you have 1 number for the whole building, quick and easy. If you have a more complicated or a larger building where you might have higher lighting power or you need decorative allowance, space by space would be the way to go. It is more complicated, more time consuming, but each space type gets a lighting power allowance, and you have decorative allowances that are included. So you generally will end up with a much higher allowance if you go space by space. Only notes here is that you must use either building area or space by space for the entire building. You can't pick and choose. Task lighting is also exempt from both models. So what does this look like from 2004 to 2016? We'll pick through, like say, an office. Small enclosed offices went from 1.1 watt per square foot to 0.93. Open plan, went to 1.1 to 0.81. So they're pretty large reduction, 26%. But you can see it varies by space type. These also get updated based on the technology that's available. So 2016 was a mixture of fluorescent and LED when we were designing these lighting power numbers. 2019 goes to 100% LED. So the numbers generally come down a little bit further for 2019. You will note that some of them have gone up, and part of that is because we rebuilt some of the models that were used to calculate the lighting power allowances, and some of them had to be updated just because they were old and had not been updated. So quickly, building area method. Again, if you have a large office, you could use one allowance 0.82, which is an amalgamation of all the space types within an office. You get one number. Very simple. Space by space looks a little more detailed in that, if you pick an office, you have a lighting power allowance, you have RCR, which we won't go through today, but if you have questions, you can ask. And then you have a whole set of control requirements. And you'll notice that they're either called required, add 1, or add 2. The way that it works is, say, for an open plan, you have to have local control, which is required. For add 1, you have to have either manual on restriction or partial automatic on. You have to have bi-level, you have to have daylighting controls, both top and side lighting if applicable. And then you also have to have either automatic full off or a scheduled off. So scheduled shut off could be a time clock, which is how most people will deal with an open office approach. So there is credit to be taken if you include occupancy sensors, for instance, in an open plan office. For smaller offices, you have to have an occupancy sensor. Automatic full off is technically a vacancy sensor. So anyway, the controls can get quite complicated, and our approach to this is to put together a large matrix as we run through, note all the space types, all the control requirements, and use that as the design tool going forward. Then there also are some related control factors. So if you have an occupancy sensor, it refers you back to this other table, which says this is the percentage savings that you should be taking for those occupancy sensors. So it's either 5 or 10% depending on the space type. Schedules. So in most cases, if you look at the 90.1 users manual schedules, in most cases, the schedules reflect the mandatory lighting controls. So you will note that the maximum, say for an office, is 65% lighting load on the schedules. That is because they assume that there's going to be occupancy sensors in most of this space. So if the proposed design does not have an occupancy sensor, then you can use the control factor to take a percentage reduction. So quite straightforward. So as an example, just quickly, there's 242-foot square office, private office that's got all these fixtures, and it has a multi-scene occupancy controller. So in that case, you fall under automatic full off. You require an occupancy sensor, so you have to have one. You get 1.1 watts per square foot, and the proposed is as per the design. You take no credit for the occupancy sensor in either model. So you have it there, you meet the requirement, no credit taken. So say a large open office, 1,200 square foot, you have 2 multi-scene controllers that are occupancy sensors. Your open plan, you can either use automatic off or scheduled shut off. So in this case, your allowance is 0.98 watt per square foot. An OCC sensor is not required because you can use scheduled shut off. In this case, we have occupancy sensors, so we can take a 5% credit below the proposed when you're doing the model. Daylight controls, these are also a little tough to run through, but generally you have to calculate the primary and secondary daylighted areas when you're doing 2013 PRM. And you have to look at how much wattage is within those primary and secondary daylight areas. If you have over 150 watts or 300 watts, you have to have stepped daylighting control. And Again, most softwares will deal with this, but if your software does not model daylight controls directly, you can use a reduction factors from that same table to account for the daylighting. So what is primary and secondary daylighted areas? I won't go into much detail, but generally it's one head height into the space is considered the primary. So, say this is 8 feet to the top of your window, this depth will be 8 feet in, and your secondary daylighted area will be another 8 feet beyond that. Where you have obstructions, obviously that would limit the amount of light that gets passed, but in general, it's one head height and 2 head heights, and you have a little bit of width to the side, 1/2 of the head height to determine the overall primary side lighted area. So you would look within this space, count up the light fixtures, determine your wattage. If it's above 150, you have to have daylight controls in there, in the baseline. So example for this, same private office in the corner, where the primary is shown in orange, the secondary is shown in green. So daylight responsive controls are required. Your controlled wattage is 162 in the primary for the baseline, so it's greater than 150 watts. So you have to have a daylight controller in that space. And you notice that these are marked by D, which is in the proposed design has it. The secondary daylighted area is only 96 square feet and has 106 watts within it. It's less than 300, so you don't have to have daylight control in this section. In this case, this one is daylight controlled, so they are taking credit for it, so you can take credit in your proposed model. So same example for the open office. Here's primary and secondary daylighted areas. In this case, both your primary and your secondary exceed the threshold, so you would need a daylight sensor controlling, in this case, 80%. Sorry, so 91.5% in the baseline. Your proposed design is only controlling 80%, so there's a slight variation in how you model. So what do the changes look like over time to lighting controls? Generally in 2004, there were some very small lighting controls allowed. Within the proposed design, baseline said no automatic controls. 2007 stepped up to say you don't model also, assuming the lighting schedules are there. 2010, again, looks very similar. Starting in 2013, you start to include these control factors where you have them. And in 2016, it sort of referenced all the way back to 2004 in the baseline. So, really 2013 was the most stringent in terms of how lighting controls were dealt with and the most complicated, I'd say. 2016 and forward, it makes it a lot simpler. You have fixed schedules. You only have occupancy sensors in very few spaces because that's what was required in 2004. Exterior lighting. So again, the main distinction in exterior lighting is you have tradable versus non-tradable surface. So tradable being things that are lighting surfaces where people are walking around and using the light for wayfinding. So, paths, walkways, stairways, landscaping, where you can trade off between those uses. And then you have non-tradable, which is in general facade lighting, which can't be traded against. So you have a maximum allowance and you can't exceed it if you want to meet the standard. And the baseline in this case will never exceed the proposed design. So, okay. One note for model, as you're doing this, if you have, say, a multi-level parking garage, there is an interior allowance for a parking garage. So your intermediate floors would be interior lighting, technically, and your upper deck on your parking garage then would be, a parking area and drive, and you would pull it off the exterior. Something we see mistakes made. Then there are some controls required. Generally, you're going to model exterior lighting at 12 hours a day. The control requirements now within the standard dictate that you need to have occupancy based or time clock control based in addition to a photocell. We haven't seen it enforced very much, but it is roughly another 6 hours of operation reduction. So anyway, that's that. So lighting. Kushagra, how are we doing on time? I think we got 30 minutes.
Yeah, I think we should end the presentation by the next 15. And
okay, I'll move quickly
yes.
through this, and I mean, HVAC could take 2 hours by itself, so I'll skip to the important things.
Do you want to quickly take a question, or?
Sure, if anybody has any lighting questions, and then, but yeah, let's do one question.
Not specifically lighting. There's a question pending long. This is by Sheikh Abdullah K. How can we adapt envelope baseline requirements for Middle Eastern countries for having energy savings? I think what he means is what baseline conditions can be replicated in the envelope for Middle Eastern countries.
It is a current research topic right now within the 90.1 envelope subcommittee. We just finished our interim meetings last Friday, but there is conversation about climate zone 0 and 1A, which affect most of the Middle Eastern countries and the hottest humid and dry climates, and that the baseline allowances are going to be examined and most likely changed. So there will be a little more leniency allowed in the envelope going forward, and that you can design around it a little bit better. It is something that is being discussed. So if you want, send me an email. I can send you the notes from the last call we had. And if you have insights into it, we'd be happy to have you on the call into the committee meetings as well. So.
Sure. So I have sent you the email address of Sam Sheikh Abdullah. Thank you for your question. I think, Sam, we can move forward in the interest of time.
Okay. Yep. So we're going to move quickly now through hot water and HVAC. And obviously, we don't have enough time to get through all of this, but again, service hot water, there is minimum efficiency requirements, again, that are given in table 742. Sort of big major things to deal with in the baseline. The baseline building will always have a separate heating system and a separate service hot water system. So if your proposed design has a combined system, which is quite common in the colder climates of the US, you can take credit for that efficiency gain against the baseline. The other thing is if you have large facilities with large heat rejection capacity, so generally we find this is applicable in hospitals or laboratory settings, you have to have condenser water heat recovery that preheats your electric hot water or gas hot water, depending what you have. So again, this is just a diagram looking at a combined system with cogen. If you have something complicated like this in your proposed design, you can take credit. Baseline will always be two separate systems. So again, the efficiency tables can be confusing here. Whether you have electric or gas heaters, it's either an efficiency factor or a standby loss. The standby loss can be a little confusing in terms of how to model it. Different softwares deal with it different ways, but be careful in the calculations. That's my one piece of advice. There's a whole lot of other things. Again, these are just references so you can look back on it, but generally you're going to have the same number of heaters, the same capacity of heaters between the proposed and the baseline. The thing that might change is you might have a fuel source difference, which we'll look at on the next table. So the baseline now is dictating the type of fuel being used to heat domestic hot water. So there could be a penalty or an efficiency gain depending on what building type you have. And again, those are based on research from the US, the most common types of heaters in specific building types. Design temperature, generally they will not be stated, but you're looking at a 140 supply to an 80-degree delta T. And flow rates, generally should be based on fixture unit calculations and demand factors, and any flow rate reductions you have. So low flow fixtures, things like that. So this is the table I was referring to. Depending on the building type, you have different water heater fuel sources. So whether you have a gas storage heater or an electric unit, you know, office is always electric now going forward from 2013. So service hot water, that was quick. And we'll keep moving. So HVAC, this is probably the most complicated section when you're doing Appendix G modeling. The way that Appendix G works is that you design your HVAC and your baseline model based on heating source. So heating source will dictate whether you have only electric as your heat source. So whether you have 100% heat pumps or electric resistance, you would fall under that category, or if you don't have any heat at all. So that also would apply for some of the hotter climates where you actually don't have a heat source, where you can actually be heating 100% from heat recovery and you don't actually require any heat input, you would fall under the electric source. Any sort of hybrid or fossil fuel type falls under that category. It also includes purchased district heat if the district heat is being generated by a fossil fuel source. So once you know your heating source, then you look at your climate zone and you look at your building type and the size of your building, and you run through a big table, which is on the next slide, which you look at the majority space type of your building, and that's how you apply the HVAC map. There are a whole ton of exceptions to this, and it can be very complicated. I would suggest if you have any question about this in terms of what the baseline system or systems should be, send an email either to your rating authority, or you could send it to the ECB subcommittee, which I also sit on, and we can, I listen in on their conversations as well. So if there's questions that come up like this, they can respond to them in an unofficial manner. Just knowing things take a little bit longer right now with the current climate. So in general, colder climates are going to be suggesting to use fossil fuels, and warmer climates are using electric fuels in the baselines. So what does it actually look like? Once you know your fuel type, whether you're electric or gas, you then look at your number of your floors and your area. So smaller buildings, 3 floors or fewer, less than 100, less than 25,000, you end up with single zone type systems. Larger buildings, you end up with, sort of a package VAV type system. And once you get to larger buildings, you end up with, a chilled water system, and either a hot water system or electric, fan powered electric boxes. So that's what the baseline is dictating now. So again, you'll see climate zones 1 to 3 are going to be looking at electric sources. Climate zones 3B, C, and then all of the colder climates tend to fall towards fossil fuel heating sources. And then there's the last one is residential. So again, there's usually a lot of questions about this and what will be the residential type. In 2013, I think it's fairly straightforward. For a residential building, you either have a PTAC, so a DX cooling system with hot water in the more moderate and colder climates, and hotter climates, you end up with a heat pump with auxiliary electric heating. So if you have purchased heat, which I guess is the one variation, you would model purchased heat in both the proposed and baseline. Again, there's a whole table of if you have purchased heat and cooling. So if you have a district energy system, there's some modifications that are made, whether you have heating only, cooling only, or purchased heating and cooling, that'll modify the baseline. I won't go through these in detail because there's a ton of permutations, but my advice is create a matrix, run through all of your systems, and make sure that you keep track of everything very well, because it can get confusing, especially for large buildings. So this is some of the exceptions when you're applying the HVAC map. There are a lot more nuances than what's just listed here, but the biggest ones that you find are the first 3 plus the computer rooms and heated spaces. So if you have, say, non-residential within a residential space, and that non-residential area is more than 20,000 square feet, you can have a secondary HVAC system. If you have, gas heating for most of your building and you have electric heating for part of it, this can also be applied. Load variation or schedule variations, generally you'll find if you have say a 24-hour supermarket within a residential building, that 24-hour supermarket would fall under exception 2, and it would have its own systems. And then similar for labs, if you have a lab that has over 5,000 CFM of exhaust, you will always have a specified system for the labs. And same with kitchens. And then large computer rooms, there's new system types that are included for those now. So if you have large server rooms, there's a separate system type. And then for heating only systems, obviously, excuse me, there's 2, system types that are heating only, whether it's gas or electric. So, and then there's, I'm not going to go through all of the dictate, but yeah, it can get very complicated. The other main thing to touch on here, and we're not going to get any further than this today, is how you assign the systems per your model. So if you have smaller single zone systems, you have one system per thermal zone in your model. When you have the larger VAV systems, you're going to have one system per the entire floor. And in this case, you can save a lot of time if you have a very tall high-rise building and you have 30 floors that are all the exact same. You can model one floor and just multiply it by 30. So there is some time saving to be included in there. So this is just what it looks like in eQuest, that you're going to have individual systems for every single zone, whereas you might save a little bit of time in programming if you have a VAV type. So I think in terms of time, that's probably all we have to get through today. Kushagra, I will turn it back over to you. Thank you everyone for listening. Sorry for droning on, but I appreciate everyone listening in. And again, if you have questions, I'm just going to go to the very end. Yeah, you'll see there's a lot of HVAC. That's obviously the most complicated piece, but we can have another whole conversation just on that. Thank you for being here, and yeah, I hope everyone is healthy and safe. So be well.
Thank you, Sam. Would you like to take a few questions now?
Sure.
So the next question is from Neeraj Yadav, who asks, please explain about thermal bridging.
Sure. So high level, thermal bridge is, when you have a uninsulated component within your envelope assembly that is reducing the overall thermal performance of your envelope. So the most common place we see this is in a, in a curtain wall type assembly where we have a metal frame that is directly attached to, the structure, and there's no insulation between the framing and the structure system. So it's a continuous metal system, and even though you might have a well-insulated, back pan in your curtain wall, the overall performance generally of these types of systems is no better than, say, an R3. You end up with similar situations when you have, mass walls where you have metal brick ties or something like that, where you end up with, metal components that are essentially transferring heat through your assembly. If you want to see some examples, I've got plenty of examples of bad thermal bridges. I can shoot some around. But again, it basically is just a way. It's the standard is moving forward to say that you need to design to remove as many of the thermal bridges out of your project as possible. So it's an education component because there's a lot of standard building practice that includes thermal bridging. And the intent of the standard is to try to educate constructors and builders and designers to understand where your thermal bridges occur and how to remove them in a cost-effective manner. So.
Thank you. The next question. This is an interesting one. In India, we generally see the energy consumption of HVAC constitutes an average of about 60% of total commercial building energy consumption. Can you share what is the breakup you have witnessed, for example, in New York, like the breakup of HVAC versus envelope versus the others? This is asked by Harsh Banu.
Okay. Let's pull. Yeah, I'll dig out some information quickly. If you want to grab to another question, I'll just grab a project and we can look and see.
Sure. Interesting question again. How much percentage of deviation will be there with actual energy consumption as compared to energy modeling? This is asked by Naresh Arthem.
That is a very good question. It can be fairly close, 5%. It could be 100% off. I guess our experience is that, the amount of time spent confirming the assumptions you're making in your model, because a lot of the what we're building in our models are assumptions, closely align with what the building will do or will see in the future. And this is it's hard. I guess it's a hard approach, because in many times, say for a core and shell type office, you won't know who the tenant is going to be, and you don't know how they're going to use the building. So you're making an assumption about how many hours a day and how many people will be in the building. So, how a building is used is something that we have a really hard time with capturing with a model. And it's not uncommon to be 30 or 40% off from actual when you're doing a design phase model, because you don't actually know what's going to happen in the building. That being said, I say it's worth it to go back and figure out why your models are wrong, and where your assumptions were incorrect, because that gives you the insight for the next time you do it to say, oh, I should have asked this question. You realize that there was something that was incorrect that you put in the model. You correct it the next time, you're going to be a little bit closer to where you should be. But again, every model is different and every building is used differently, until you actually get into a post-occupancy type situation where you can look at utility bills and you can start calibrating a model. You're taking a fairly large guess. So, I think for the purposes of 90.1 and the standard gives you a fixed guideline to estimate how much better you would be than a reference building. And I think for that purpose, it is very good. And it's good for testing, efficiency improvements, to know a relative savings percentage against a reference building. So, if you're going to improve your envelope, it's probably pretty good at telling you, that triple pane glass will save 6% energy cost compared to double pane glass. What it's not going to tell you is the magnitude of that in terms of dollars per square foot, say, of operating cost. But it will give you a relative savings percentage. And that's, I think, where, it's most critical to inform the people that are using the results of the model to help them understand that you're not trying to predict their utility bills down to, a precise accuracy, $1 off or whatever. It's very difficult to do that. And I can't, I wouldn't find anybody that does energy analysis that would tell you that you should use a ASHRAE 90.1 model to try to do that. But yeah, it is good for design, and it is good for relative performance. And that's, I think, I think that's the misconception, is that these models are meant to be accurate to current operations when they're really not. And I know there's a lot of media out there that has said, oh, look at how bad, look at how far off these models are. you know, it's context, and that, you know, the models were not meant to be predictors of energy consumption. They're meant to show relative performance to a fixed design with a fixed set of assumptions. So if you're looking for actual performance, you really need to get into calibration, and you need to look at actual operating schedules and, you know, how people actually use a building, which, yeah, I mean, that's 80% of the work we do is that, and it's, yeah, it's a much different approach than doing 90.1. Kush, you still there?
Yeah, so we have an interesting question. I'll just read it out. We shouldn't answer it. Can UV lamp protect from coronavirus? This is from Diarul Islam Munshi. I don't think we are in a position to answer that right now as a part of this webinar, but I hope we arrive at some answers from the community.
Yeah, the only
Next
thing I'll say
question.
is I know
Yeah,
people are,
yeah.
there was conversation on Friday. There's a, you know, there is a group within 90.1 that looks at UV as a method of cleaning air, and yeah, they're inconclusive at this point, but it is something that is being looked at as a possible way of decontaminating surfaces. They're not really sure if it works for airborne travel of the coronavirus at this point. So yeah, keep going.
I think we'll take one last question for the day. Thank you for being patient with answering so many questions.
Yeah, of course.
The question is, one second, which is more sustainable between gas heating and the heating by heat pump for hot water usage?
That's a loaded question. I mean, I think the trend that we're seeing now is that, at least in North America and in Europe as well, actually, is that people are moving towards electrification. And when I say moving towards, I say it's a long-term plan. People are thinking about it. There are communities, obviously, that are way ahead of the game. You know, you look at, say, Denmark, for instance, you know, parts of the Netherlands, Germany, that have already really gone down this path. And because electric energy production has a very low carbon content in those places, you know, where they have a large percentage of renewable energy that's producing their electricity, it seems that it makes sense to be on electric based heating systems there. You know, I'll say in you know, the US and North America generally, you know, there's still a big push by oil and natural gas lobbies to use natural gas or oil in buildings for heating, and it's still relatively cheap. So, you know, I think in the current trend, it's you're still going to see a mixture of it. I will say New York City, you know, is also looking and thinking about the same topic, in that, you know, people are now planning for electrification. Like, they're looking at, okay, we're going to build this building now. What does it mean, say, in 25 years from now? How would we, you know, modify the building to be electrified? Or they're doing a retrofit and they're saying, you know, what would it require to put heat pumps in our building? And, you know, there's restrictions and limitations to doing that, right? Like, a big boiler system is very well set up to do, you know, a 50, 60, 70, 80 story building. You pump hot water and you have multiple boiler sets. You know, heat pumps are a little tougher because you have to have distributed heat pumps throughout the building. You're going to end up with, you know, limitations. You can't do refrigerant-based systems on large buildings like that. You know, there's space planning issues. So hard to say. I mean, I think electrification, you know, 10 years from now will be, you know, heat pumps will be much more common. And I think the standard will move that direction. But again, that's just my opinion. I don't know. I mean, I think as the electric grid becomes more efficient and less carbon intensive, heat pumps will be more and more common. My opinion.
Right. Thank you, Sam. I think this is very informative. Thank you for your time. This is, I know, super early morning, and thank you for making all the effort. We're getting great feedback. I'll just hand over to Mani. Mani, are you there? Can you hear me?
Yeah, yeah. Can you hear me?
Yeah, we can hear you. Please take it over from here.
Yeah. So at the end, the presentation is over and webinar is about to an end. So once again, we would like to thank you everyone for all of your support and the participation in today's webinar. And in addition, we also would like to thank Mr. Sam, who has spared his valuable time and shared his valuable and very insightful information regarding ASHRAE 90.1 with all of the participants who are attended from various countries, India, Pakistan, South Africa, Dubai. I can see many people from here, and Nigeria. So many people who are attending and from RAL, even ASHRAE region at large. So there are around 25 chapters in ASHRAE RAL, and I can see around 8 to 10 countries have been participated in this today's webinar. So yeah, we are so grateful for your support, and without you, this wouldn't be possible. And keep participating and learning with ASHRAE Chandigarh. And this was organized by ASHRAE Chandigarh in association with the ASHRAE Rajasthan, which is supported by ASHRAE Jaipur chapter. And in addition, we also would like to thank ASHRAE Rajasthan team, Mr. Ashu Gupta, who have been connected with us, Mr. Kushagra Juneja, who have been supporting from initial, from marketing and preparation and connecting with the speaker till the completion of this webinar. And Mr. Kishan Khatri from ASHRAE Jaipur chapter, who have provided his extended support to make many people aware about this webinar. And yes, we are organizing our next webinar on 1st of May 2020. So yeah, please note it. It would be a very great and insightful webinar, which is a panel discussion on COVID-19 opportunities for sustainable development. So there is a panel from 8 countries representatives, and will discuss on future sustainable development opportunities. So see you all there, and subscribe to this ASHRAE Chandigarh YouTube channel if you have any queries related to the presentation or anything, that we will share it on our YouTube channel only. So all the requirement will be fulfilled through this channel. And at the end, we also thank all our sponsors who are annual technology partners and annual partners who are Armacell and FlowGuard and BlazeMaster. Even in the annual partners are Aerolem, MaxFlow, Jeevandeep, Metal Joints, and GL Insulation. So they are supporting us, and through by the support of the all, and we are organizing this series of webinars. And yes, you can note down our upcoming as after 1st of May, which is on the green building or sustainable development goals. We are organizing on 1st of May, and in series to it, it is next is on 5th of May and 9th of May, majorly for building emotional intelligence and building CFD. So stay in touch and stay tuned for next 1st May panel discussion, which is, I'm sure, very much relevant to all of you, and it would be a great hit with all of your support. Thank you very much for all you all who have attended this webinar today. Thank you very much.
Thank you, Mani. Appreciate it.